Hey, welcome back. In this video, we're going to talk about one of my favorite proofs. This proof is known as the Marcus-Tardos theorem, and it is the proof of the Stanley-Wilf conjecture. This proof uses a bunch of things that we've covered in this class, including 0-1 matrices, decrease and conquer, pigeonhole principle. There's even some induction at the end of the proof, and there's also some binomial coefficients used in the proof. So a bunch of different topics that we covered in here. And one topic that we also covered, which is kind of the main topic of the whole problem, is permutations. So the Stanley-Wilf conjecture is a problem about permutations. And more specifically, it's a problem about pattern avoidance in permutations. So we've talked about pattern avoidance in a few different structures. We talked about it in graphs, we talked about it in 0-1 matrices, and now we're going to talk about pattern avoidance in permutations. So in order to define what it means for one permutation to contain or to avoid another, we define this term relative order. And we say that two sequences of numbers of the same length, so both these sequences that I've drawn in this first bullet have length m. So the first sequence is a1, a2 up to am. The second sequence is b1, b2 up to bm. And we say that these sequences have the same relative order if ai less than or equal to aj, if and only if bi less than or equal to bj for all I and j. So for example, here in the top left are two sequences with the same relative order. So those two have the same relative order. Here are another two with the same relative order. And then over here are two sequences that do not have the same relative order. So with these last two sequences, we can see that this first sequence, if this is our A1, A2, A3, B1, B2, B3, we can see that we have A1 less than or equal to A2 and B1 less than or equal to B2. And we can see that we have A3 less than or equal to A2 and B3 less than or equal to B2. But we have A3 less than or equal to A1, but then we have B3 is not less than or equal to B1, because B3 is 4 right here, B1 is 3, 4 is not less than or equal to 3. So that's why these two do not have the same relative order. And if we're given a permutation pi of the numbers 1 up to k, so for example, if we had k equals 3 here, an example of pi would be the permutation 1, 3, 2. And that permutation I drew right there, that represents pi sends 1 to 1, pi sends 2 to 3, and pi sends 3 to 2. So we can represent permutations multiple ways. We can draw them as sequences. We can write them as maps like this. And we say a permutation pi of 1 up to k is contained in some other permutation sigma of 1 up to n. So sigma contains pi if some subsequence of sigma has the same relative order as pi. And for this definition, we should definitely look at some examples. So I'm going to draw some over in this margin. So let's consider pi, for example, right here. Pi equals this permutation, 1, 3, 2. And let's say sigma right here is the permutation 1, 3, 5, 4, 2. Now we can find a subsequence. A subsequence of sigma is what we need. And it has the same relative order as pi. So for example, here is one subsequence that works. We could take the subsequence that is the exact same letters as pi. So we could take 1, 3, and 2. And that means that sigma contains pi. Let's consider one that's less obvious. So we can take one here. Let's do alpha. And this will be okay. So now if we try to take the same letters as pi in alpha, if we look at for the 1, 3, and the 2, they're in the wrong order. So it's not the same relative order if we go for the 1, 3, and 2. But we don't have to go for the 1, 3, and 2. We can go for different letters that have the same relative order. So for example, we could go for the 3, the 5, and the 4 right here. And we can see that 1 less than or equal to 3, 3 less than or equal to 5. So the A1, A2, A3, B1, B2, B3. So we have A1 less than or equal to A2, B1 less than or equal to B2. We also have A1 less than or equal to A3, B1 less than or equal to B3. And we also have A3 less than or equal to A2 and B3 less than or equal to B2. So that subsequence of alpha has the same relative order as pi. So we can say that alpha contains pi. Now, if a permutation does not contain pi, we say that it avoids pi. So for example, here's one that avoids pi. We can say that beta, which equals 1, 2, 3, 4, 5, that one avoids pi. There is no subsequence of that of length 3 that has the same relative order as pi. And another one that avoids pi, let's call this one theta. So 5, 4, 3, 2, 1. There's no subsequence of that that has the same relative order as pi, so that also avoids pi. And again, just to emphasize, this is our pi up here. So 1, 3, 2. So that's a permutation of the numbers 1, 2, and 3. So this is a k equals 3. And we did a bunch of examples. So this is just an intro to pattern avoidance and permutations. And one of the most natural questions we can ask about pattern avoidance and permutations is how many permutations are there that avoid a given pattern? And that's the topic of the Stanley-Wilf conjecture. So given some permutation pi, like on the last slide, our pi was 1, 3, 2. we define this function, big U sub n of pi, to be the number of permutations of 1 up to n that avoid pi. And Stanley and Wilf, their conjecture was that for every permutation pi, there exists some constant c such that U sub n of pi is less than c to the n for all n. So I wanted to do a small example. So we can consider a real simple pi here. We can say pi equals 1, 2. So if we want to avoid pi, we want to avoid having a subsequence of length 2 where the element to the left is less than the element to the right. So the element to the left less than the element to the right. We want to avoid that. How can we avoid that? The only permutations that avoid pi, they can't be increasing anywhere. So if they have two adjacent elements in the permutation where there's an increase between those elements, that would contain pi. We're trying to avoid pi. So in order to avoid pi, you can't have any increases. In other words, the only permutations that avoid pi are what we call decreasing. So for example, if we're looking at a permutation of 1 up to 3 that avoids pi, the only one that does that is 3, 2, 1. So that's n equals 3. N equals 4. The only permutation that avoids pi is 4, 3, 2, 1. And it keeps on going. So up to any n, it's just n minus 1 down to 1. So you can see for this permutation pi here, for this permutation, the function U sub n of pi is easy to calculate. It's just 1. And we can also consider the permutation, if you consider the permutation 2, 1, that one's the same. It's going to have U sub n of pi equals 1. Already though, if we look at a permutation with an extra number on the end, so for example, 1, 2, 3, already that one becomes exponential. And Stanley and Wilf's conjecture is that regardless of the permutation, no matter how large this fixed permutation pi gets, even if pi had 1,000,000 numbers in it, the function U sub n of pi right here will still be exponential. It just might have a larger constant c as the base of the exponent. This conjecture was a really big open problem. It was open for decades. And there was some incremental progress over time, which I want to discuss before we get to the main result, the Marcus-Tardos theorem. So one of the most important pieces of progress on this problem was known as the Furedi-Hajnal conjecture. And this is what led to the idea of the Marcus-Tardos theorem. So the Furedi-Hajnal conjecture is a problem about 0-1 matrices, something that we've seen a bunch of before. And remember, in our earlier videos on 0-1 matrices, we defined this extremal function, ex of np, to be the maximum number of ones in an n by n 0-1 matrix that avoids p. And the conjecture of Furedi and Hajnal was that this extremal function, ex of np, equals big O of n for every permutation matrix p. In other words, the extremal function has a linear upper bound in n for every permutation matrix p. That was their conjecture. And Klazar showed that this conjecture, if it was true, would imply the Stanley-Wilf conjecture. So for the remainder of this video, I want to talk about why Klazar's result is true. And then in the next video, we'll actually prove the Marcus-Tardos theorem about permutation matrices, which implies the Stanley-Wilf conjecture. So this is what Klazar showed. Klazar showed that if the Furedi-Hajnal conjecture is true, then that implies the Stanley-Wilf conjecture is true. And in order to see this, we need a little bit more terminology. So we're going to define this function. Given a permutation pi, the function m of pi will output the permutation matrix that corresponds to pi. And we can say that a little more specifically. So this matrix m sub pi will have all of its entries 0, except the ij entry of m of pi will be 1 whenever pi of I equals j. So let's look at an example. Let's consider pi equals 1, 3, 2. And let's also consider another one. We'll do sigma equals 1, 2, 3, 4. Now let's do m of pi first. I'll do this one in the margin. So the m of pi, it's going to have all zeros except for ones in the entries where we have pi of I equals j. So in pi, we have pi of 1 equals 1. That means the 1, 1 entry of m of pi will be a 1. And we have zeros in the 1, 2 entry and in the 1, 3 entry, because pi of 1 is not 2 and it's not 3. Now, pi of 2 is 3. So in the 2, 3 entry, we will have a 1. But pi of 2 is not 1 and it's not 2, so we'll have zeros in these entries. And finally, pi of 3 is 2. So we'll have a 1 in this entry and zeros in these entries. And now I'm going to do that m of sigma matrix. And this one's slightly easier to draw. It's going to have a diagonal of 1s. And the rest of the entries are zeros. And you know what's interesting here? You can look at these matrices and you can see that m of sigma avoids m of pi. And similarly, up here we can see that sigma avoids pi. So the permutation sigma avoids the permutation pi, and the permutation matrix m sub sigma over here avoids the permutation matrix m sub pi over here. And that's interesting. And there's the example I was going to draw. So here's a problem related to this example I just drew. Prove, in general, that for any two permutations pi and sigma, pi avoids sigma if and only if m of pi avoids m of sigma. Now we're going to look at Klazar's argument to prove that the Furedi-Hajnal conjecture implies the Stanley-Wilf conjecture. So we're going to define this set of n by n 0, 1 matrices. We'll call the set T sub n comma p, and it's going to be the set of all n by n 0, 1 matrices that avoid p. So T sub n comma p, it has these two parameters, n and p. The n is telling us the size of the matrices in the set, they're n by n matrices, and the p is telling us that those matrices avoid p. Now, we can note that T of n comma m sub pi, it must contain all of the n by n permutation matrices that avoid m sub pi, because it's the set of all n by n 0, 1 matrices that avoid p. So if it contains all of the n by n 0, 1 matrices that avoid p, it must contain all of the n by n permutation matrices that avoid m sub pi if p equals m sub pi here. So here we have p equals m sub pi. So permutation matrices, these are 0, 1 matrices. So this set T of n comma m sub pi, it must contain all of the n by n permutation matrices that avoid m sub pi. And that means that this function u sub n of pi is less than or equal to the cardinality of the set T sub n comma m sub pi. So recall this function, the u sub n of pi. This is the number of permutations of 1 up to n that avoid pi. And we showed on the last slide, or I left it as a problem to you, to show that for every permutation pi and every permutation sigma that avoids pi, the permutation matrix M sub sigma must avoid the permutation matrix M sub pi. So all of those permutation matrices M sub sigma are going to be in this set T of n comma M sub pi. So all of them are being counted in this cardinality here. And that means that all of the permutations that are counted in this quantity, the number of permutations of 1 up to n that avoid pi, each of them has a permutation matrix that is included in this set T. So that's why we can say the quantity we're trying to count, u sub n of pi, the quantity we're trying to count for the Stanley-Wilf conjecture, this is less than or equal to the cardinality of this set T sub n comma m sub pi. And now we're going to prove Klazar's claim. If the Furedi-Hajnal conjecture is true, then the Stanley-Wilf conjecture is true. And in order to prove this claim, we're going to prove an inequality. So this is what we're going to prove, and it's going to imply the claim. So how can we prove this? Well, in order to prove this, we can define a map. So earlier in the semester, when we were looking at problems where we wanted to prove that two sets had the same cardinality, we defined a bijection between those sets. Here, we're not trying to prove that two sets have the same cardinality, but we are trying to compare the cardinalities of these sets. We're trying to say that the cardinality of the set on the left is at most the cardinality of this set on the right times this factor, 15 to the extremal function. So in order to prove this, we're going to use a similar idea to what we were doing earlier in the semester. Instead of defining a bijection, we're going to define a map. And the map, we'll call it F. The map is going to go from the set on the left right here to the set on the right. And given any element of that set on the left, so those elements of the set on the left are 2n by 2n, 0, 1 matrices that avoid P. And we define the output of this map F on the element. So we say F of A. And we define it by partitioning A into n squared contiguous blocks of dimensions 2 by 2. So I think it might be useful to look at an example here. So let's say we have A right here. I'm going to do maybe a 6 by 6A. So there's A right there. And A, we're saying, is an element. A right here is going to be an element of T sub 6 of P for some P. And we're going to partition A into n squared contiguous blocks of dimensions 2 by 2. So here our n equals 3 because 2n was 6. 2n is the 6 right here. So here's our partition of the rows and then the partition of the columns. And so we have a total of n squared blocks there because we have 3 squared, so 3 by 3. So a total of 3 squared blocks. Each of the blocks is 2 by 2. Then we define this map from A to a new matrix. And this new matrix is going to be an n by n matrix. So A here was 6 by 6. We're going to a 3 by 3 matrix. And each entry of this 3 by 3 matrix is going to correspond to a block from A. And in order to obtain the entries of the 3 by 3 matrix, we'll replace any all 0 block from A with a 0 entry in the new matrix. And any block that's not all zeros, in other words, any block that has any ones at all, we will replace it with a 1. So this top left block gets replaced with a 1 because it has some ones in it. The 1, 2 entry of the new matrix, this is going to be 0 because this block up here was all zeros. The entry to the right of it, it's going to be a 1 because there is a 1 in this entry right here. Now here we have a 1 because there's a 1 right here. We also have a 1 here because there's a 1 in that middle block right here. We have a 0 over here because there's all zeros in that block. And a 0 down here because the bottom right block is all zeros. And a 0 down here because the bottom left block is all zeros. But the bottom middle block, that has some 1s, so the entry corresponding to it down here gets a 1. So given a matrix A in T sub 6 of P, the claim is that this matrix is in T sub 3 of P. But how do we know it's in there? How do we know that matrix is in T sub 3 of P? What does it mean to be in T sub 3 of P? Well, to be in T sub 3 of P, it has to be 3 by 3. So that's clearly true. The matrix we got is a 3 by 3. But why does it have to avoid P? That's the other part of the definition. So in order to be in T sub 3 of P, we have to avoid P. In general, to be in T sub n of P, we have to avoid P. So this map, it clearly takes a 2n by 2n matrix to an n by n matrix. But why does the new matrix have to avoid P? And the reason for that is because the original matrix, A, avoided P. And if we did have a copy of P in the new matrix, P right here is a permutation matrix. So there's no row or column in P with multiple 1s. So there's no row or column in P with multiple 1s. So if we had a copy of P in this matrix down here, the smaller matrix that we obtained from A, then we would be able to form a copy of P in A, because the 1s in the copy of P in this smaller matrix represent 1s in the copy of P in A. So the new matrix has to avoid P, or else the original matrix would have contained P. So the new matrix, if it contained P, the original one would contain P. Thus, the original one avoiding P means the new one must avoid P, like contrapositive. And here's a problem now for you to think about. And this is really the heart of this argument. So prove that for any matrix in this set, so the set that we're mapping to, so the set of the smaller matrices, prove that for any matrix in that set, there are at most 15 to the ex of np elements of the larger set. This should be a T sub 2n of P that F maps to this element. So this map that we defined right here, the map F, it goes from T sub 2n of P to T sub n of P. And prove that for any element on the right side, there are at most 15 to the exnp elements on the left side. So this is the left, this is the right of the map, and prove. So you can think of it like this. If we have our left side, here's t n of p, t sub 2 n of p, and we have our right side, t n of p, and we have our map f right here. And we have a bunch of elements mapping to the same one. So we're saying all of these map to this one right here. So if we say that there are x sub L of these elements that are mapping to this single one over here, we're trying to show that L is less than or equal to 15 to the ex of n comma p. So the number of these elements on the left that map to any single element on the right is at most 15 to the ex of n comma p. So that's what I want you to prove. And I want you to prove that using the definition of our map here. So our map, we replaced any all zero block with just a zero entry in the new matrix. So if we see a zero entry in the new matrix, then we know it corresponds to an all zero block. Now, any other blocks we replace with a one entry. So if we see a one entry in the new matrix, there's multiple choices for what the block was. So any one entry in the new matrix corresponds to a non-zero block, a non-all zero block in the larger matrix. And remember, these blocks are 2 by 2. So a 2 by 2 block, how many ways can a 2 by 2 block have not all zeros? So 1, 0, 0, 0, that doesn't have all zeros. 1, 1, 0, 0 also doesn't have all zeros. 1, 1, 1, 0 also doesn't have all zeros. 1, 1, 1, 1 also doesn't have all zeros. So any of these don't have all zeros. And there's other ones we can do as well, like 0, 1, 0, 0. So you need to count how many of these are there that don't have all zeros. The only one you're trying to avoid of these 2 by 2 blocks is this one. This is the only bad one. So that's a hint for this problem to think about. So that's going to at least tell you why we're getting the 15 here. And then this exnp right here. So this exnp, the maximum number of ones in an n by n matrix that avoids p. So we know exnp is the maximum number of ones in any element of this set right here. So this set tnp, the set of n by n 0, 1 matrices that avoids p. So we know any n by n 0, 1 matrix that avoids p has at most exnp ones. So that's a connection to tnp right there. So see if you can take that connection and take the connection with the 15 and the number of these 2 by 2 matrices that are not all zeros, and see if you can prove this bound right here. So that's a problem for you to think about. And there's a little bit more in the slide, so I should erase a little. So based on that problem, we can say our map F, for any element on the right, there are at most 15 to the exnp elements on the left that map to it. So the size of the left is going to be at most the size of the right times that factor right here, 15 to the ex of n comma p. So that's why we define this map. So we could say that the size of this larger set, the t sub 2n of p, is at most this factor, the maximum number of elements to get mapped to any element on the right, this factor times the size of the set on the right. So that's how we got this bound. And you can think of this bound as following from pigeonhole principle, because if we had the size of the set t sub 2n of p being more than this, then by the pigeonhole principle, there would have to be some element of this set, the set on the right, which has more than this number of elements on the left that map to it. So that would be true by pigeonhole principle. So we can say by pigeonhole principle, we get this upper bound. And here is another problem for you to think about. So I said that we would prove this claim, and it would follow just from this inequality right here. And I've left that problem to you, but I'll give you a hint to think about it. So prove this claim that if P is a permutation matrix for which the extremal function of n comma P equals big O of n, then there is a constant C such that this should say U sub n of P. Whoops. So that should not be a T. U sub n of P is less than C to the n for all n. Actually, T sub n of P is fine there, but it should say cardinality of T sub n of P. Yeah, so T sub n of P is less than C to the n for all n. So that's fine. So that's a problem for you to think about. If P is a permutation matrix with the extremal function of exnp equal big O of n, then there's a constant C such that the cardinality of T sub n of P is less than C to the n for all n. So just the cardinality there was missing. And let me give you a hint on this. So where does this factor into things? Well, if ex of np equals big O of n, we would be able to say that there is some constant C such that ex np less than or equal to C times n. And if we can say that, then we could take this inequality right here, and we could write cardinality of T sub 2n of P is less than or equal to cardinality of T sub n of P times 15 to the C to the n. And so the question is, and maybe I'll give this constant a different name because we have a C down here. So I'll call this one D. This will be a D up here. So can you find some constant C in terms of D? So C can be very large. It just has to be some constant in terms of this constant D over here. So can you find a constant C in terms of D such that the cardinality of T sub n of P is less than C to the n for all n? Now let me mention one other hint besides this part right here and this. So if you want to get this for all n from this, which is an inequality which relates 2n to n, one way you could try to prove this would be induction. And I won't say what kind of induction here, but you know that there is a kind of induction that if the other kind works, then this kind has to work. So you might as well go with the one that's going to work. So I'll leave you with that problem to think about. And in the next video, we're going to see the rest of the proof of the Stanley-Wilf conjecture. So let's look at what we still have to prove. So here's the problem for you again. So this problem is for you to prove. And again, this problem, there should be a cardinality there that's missing. But other than that, it should be fine. So prove that if P is a permutation matrix for which the extremal function of P is big O of n, then there exists a constant C such that the cardinality of T sub n of P is less than C to the n for all n. Now, like I said, in the next video, we're going to finish off the proof. So what we're going to do is we're going to show in the next video that this assumption in this problem, we didn't need to even write it. So if we have the fact that P is a permutation matrix, already we can say for any permutation matrix, the extremal function is big O of n. So this part is redundant. It was not known to be redundant for a long time. So it wasn't until around like 10 to 15 years ago when it was proved that this was true. And this conjecture was open for decades before that. So we're going to prove in the next video that the extremal function of every permutation matrix is linear in n. So that means that this hypothesis in this problem was redundant. And this theorem that every permutation matrix has a linear extremal function is known as the Marcus-Tardos theorem. And as we noted on an earlier slide, right here, this function, the number of permutations of 1 up to n that avoid pi, that function is less than or equal to the cardinality of the set T sub n comma m of pi. And this is true for every permutation pi. So we observed that in the earlier slide. And that tells us then that if we can say that the extremal function of exnp is big O of n for every permutation matrix P, then we can say that Tn of P, the cardinality is going to be less than c to the n for all n for some constant c in terms of P. And then that implies that we can take P equal to m of pi, and we can say there exists C such that the cardinality of T sub n of m of pi is less than c to the n for all n. And that's the quantity we have on the right here. So if we can just show this bullet, then we get u sub n of pi is less than c to the n for all n for some constant c. And that's what we want. That is the Stanley-Wilf conjecture. So we will prove that last part, this bullet, in the next video. And that's all we have left besides the problems that I've left you to think about. And that's it for now, I think. Thanks for watching.